All right. I've tried to draw this while I'm recording a couple of times now, and I just didn't like the way it looked each time, and I just said, you know what? We're just going to draw this thing out. It'll be fine. Okay. So here's what we got. These guys are going to be, I've got two, what we want to do, what are we looking for, Steve? Find the moment of inertia for the shaded region, find the moment of inertia about the x-axis for the shaded region. All right, so these circles, how we would normally define circles, because these are actually holes that have been cut out of this shape, we would normally define the center of those holes because that's where we're going to locate those to be drilled out or machined out. So that's how I'm going to define these. I'm going to define these similar to how we would in normal engineering drawings, so different than what you might see in the textbook. So I'm going to define where the center of this location of this hole is. So that's 1, 2, 3/4 plus an 8. So that's 6, 7. That's going to be 7/8 of an inch from that edge. And the same thing over here. Maybe not the best way to define it, but it's symmetric. So we're also going to define this. I could put a line of symmetry through here, but you know what? We're just going to say that's 7/8 of an inch from that side. This is 1 inch up from the bottom. That's 1 whole inch up from the bottom. And then it would be 3 inches more to get to the top. It's 4 inches tall. And this frame then is 3 inches wide. Would be the shape. And these diameters, we would call them out like this. We would have, I've got 2 shapes here. It'd be 2 at, and these are 3/4 inch diameter. You might see something like that, or rather than at, it might say 2 times. So you've got 2 circles here. Each of them are 3/4 inch diameter. It's not perfect drawing, but closer to what we might see in a technical drawing format. So, and I've mixed up here. I'm saying inches. I should just be consistent. Say inches the whole time, or I should say hatch marks the whole time. I should be consistent and not mix those up. And 3/4 inch diameter. Okay. So we're going to find the moment of inertia about this x-axis along the very bottom of this thing for this whole entire shape, for the shaded region. Okay. So I've got circular holes have been cut out here. All right. So I'm going to break this down into 3 shapes. I'm going to have this large rectangle. I'm going to have 2 circular holes have been cut out. Okay. So let's work for the solid rectangular region first. So we get this shape number 1. We'll know about its x-axis. Now, it's going to have its own centroid, x prime, if you will. This is 2 inches up to there, and 2 more inches up to the top. 3 inches wide. Now remember, for a rectangle, the moment of inertia about its own centroidal axis, we said was bh cubed over 12. I want to know the moment of inertia about this x-axis. So it's going to be the moment of inertia about its own centroid axis plus a d sub y squared. Well, this distance here is 2 inches, you can see. Okay. So that should be easy enough to calculate. Ix is equal to, and I'm going to do this before I actually plug numbers in. I'm going to do it this way. I'm going to say it's bh cubed over 12 plus the area being the base times the height. In this case, the d sub y is going to be half of the height, h over 2. And that's going to get squared. Because I want you to see there's actually a formula I could use here that's always going to be true. This is bh cubed over 12 plus this is bh cubed, and this is over 2 squared is going to be 4. So this is over 12, and this is over 4. So this would be 3 over 12. So it's going to be 4 over 12 BH cubed, or BH cubed over 3. For any rectangle, if I want to know the moment of inertia about the bottom edge of any rectangle, you could do this and drive it out. You're also welcome, I've already done the algebra for you, you're welcome to, anytime I've got a rectangle, I want to know the moment of inertia about its bottom axis, the edge axis, is going to be BH cubed over 3 instead of BH cubed over 12 for its centroidal axis. So we just plug in now, right? The base, 3 inches, the height, 4 inches. That's going to get cubed, divided by 3. I don't know what that is. I'm going to pause. Let's find out. All right, I got 64 inches to the 4th. Again, what is, Steve, what the heck are inches to the 4th? I don't know. It's just a moment of inertia. It is what it is. It's kind of abstract. It represents the resistance to this thing to rotate about this axis. That's about all we got for you. Right? At least for right now, that's about all I've got that would make any sense. Let's find it for these 2 circular holes. And again, that's for the shaded region. So I found the overall region. I need to find the moment of inertia for these 2 holes, and I'll subtract it from this moment of inertia if the whole thing was just solid rectangle. So let's do that. So moment of inertia then for shape number 2, which is negative, and shape number 3, which is also negative because these are holes. To the center of those holes, down here to the x-axis, is going to be 1 inch. That's given on the initial diagram. Right? 1 inch up to the center of those 2 holes. And so that's going to be my d sub y. It's going to be 1 inch. Okay. Now I'm going to go pull my book, and then we're going to look at moment of inertia for a circle. So here we are, moment of inertia for a circle. So the area, of course, is pi r squared. Moment of inertia about either the x or the y-axis is going to be dictated only by the radius, 1/4 pi r to the 4th. So I'm going to pause here and pick that up on the next page. All right, moment of inertia about the centroid axis. That would be up here, x prime. For a circle, it's going to be 1/4 pi r to the 4th. Okay, so Ix prime for 2, which is going to equal to Ix prime for 3, is going to equal 1/4 pi. The radius, well, we said the diameter, which is what engineers actually work with, is going to be 3/4. I need half of that. And then that whole thing gets raised to the 4th power. And so I've got a complex fraction there I'm going to have to deal with. And then again, that's the moment of inertia about this axis, the centroidal axis through those circles. I need to know the moment of inertia about this axis down here. So Ix2, which is going to be the same as Ix3, is going to equal this Ix prime 2 plus the area of 2 times d sub y for 2 squared, and it's the same for both 2 and 3. They're both the same area because they're the same diameter, and they're both the same distance from this x-axis, d sub y. Okay, so this is going to equal what I've got here, 1/4 pi times quantity 3/4 divided by 2. You call that 0.75 inches divided by 2 if you like. That might be better. That's going to get raised to the 4th power. Plus pi times the area is going to be pi r squared. So the area, the pi times 3/4 divided by 2, and that's going to get squared. And then multiplied by 1 inch, also going to get squared. These 3/4 are all inches. Okay, let's run numbers. Be right back. All right, and this is what I've got. So for both shapes, 2 and 3, this is their moment of inertia. Okay, and what are we trying to do again? Well, remember, we've got this shaded area. I've got this rectangle, which I found the moment of inertia for that whole rectangle if it was solid. But I've drilled out 2 holes here, and I found the moment of inertia for each one of those holes here. So since those holes have been removed, we need to remove that moment of inertia from the total 64 up above. So the total moment of inertia about this x-axis is going to be the moment of inertia about the first shape minus, because it's negative because it's a hole, moment of inertia about the second shape minus the moment of inertia for the third shape. And if we run that out, I've got 64 minus 2 times this guy. And I just realized, I'm sorry, I've not kept this on the screen for you. Here we go. So if I run these out, run the calculations, I get 63 point, we'll say 1 inches to the 4th. Again, I know that's kind of an arbitrary value. It's like, Steve, what does this actually mean to me? And again, we're showing you a tool, a bit of information that you're going to need in later courses, even if it seems a bit abstract for you right now. This is IX way up here. This is IX1 for the first shape. Here I found for 2 and 3, and there we are. All right, guys, hopefully that'll get you armed with the homework that you can actually go tackle that. Let me know what questions you have, what troubles you run into.